Welcome to the Open Stacks text, Chapter 11, Fluid Statics. This is recorded for Aquinas University's Physics Without Calculus class. We'll be going, as I said, over Chapter 11, Fluid Statics. Fun part about this chapter is it's not super connected to what we've done previously. I'm not building on previous equations as much as I am presenting the equations in very, I would argue, simple forms and going over them. I skip over, as I say every time, some of the questions from the text. So if you're working through this and the example I gave doesn't quite land for you, go back to the textbook and go over the other examples in the text. That's only going to help you solidify understanding of the subject. A fair amount of this chapter is also, I would say, not mathematical, right? Conceptual conversations. And again, I'll be going over those more in brief. Feel free to read the text. The text is pretty good for free at explaining these concepts. With that all being said, let's start with Chapter 11, Fluid Statics. So, what is a fluid? When I say fluid, most people probably picture water, liquid, but that's not really the full encompassing of the word fluid. Fluid and liquid are not synonymous. They're not two ways of saying the same thing. Matter, of course, can come in a large variety of phases, of types. The classic three: solid, liquid, gas, everyone knows. Most people probably associate plasma as a form of matter, which is true. In reality, it's like 8 or 10 different forms of matter. We're discovering new stuff every day, but most of those are by and large irrelevant to our day-to-day lives. The way we distinguish the matter is as shown here by how the particles interact with each other, essentially. A solid, the particles don't really move in relation to one another. As shown in the picture, they're kind of on springs and they will vibrate more than move, the particles. A liquid, the particles have some motion, and a gas, the particles have some more motion to them. B and C, and to an extent D, plasma, are what we would consider our fluids. Fluid, the way to define a fluid is that it flows. That's the easiest way to define it. When you have your warm house and you open the door, the warm air flows out of it. That's literally what happens. Wind is air that is flowing. So liquids and gases and plasma, though I'm going to stop talking about plasma now, are all considered fluids. Anyone that's worked with hydraulics knows you can have air in your hydraulics or you can have liquid in your hydraulics, and it's still going to do the same thing. We're going to get to Archimedes' principle at the end of this chapter and go over hydraulics, actually. But to reiterate, a fluid is something that can flow. Is there more to it? Yes. Is that relevant? No. That's the working definition we're going to use here. A fluid's ability to flow plays a factor in a variety of things, including your basic descriptors such as area, mass, volume, stuff like that. The picture shown here is showing that difference. Mass is gravity's effect on something, right? Weight, mass, more or less the same thing in most scenarios. Volume can play a factor in that, and those two combine to form density. How dense something is how massive it is compared to how much area it's taking up, or its volume. So a ton, right, is a measure of weight or measure of mass. And if two things each weigh a ton, they weigh the same. A ton of feathers, or here a ton of straw, and a ton of bricks both weigh the same. They don't look the same. Straw is obviously a lot lighter than brick, but the ton is a measurement purely of the force gravity is pulling them down with, nothing else. And that plays a big factor into fluids, because fluids can be pretty heavy, right? If we go back up here, solids usually are the most dense object because you have the most particles in a given area because they're not able to go anywhere else. Liquids can also simultaneously be very, very, very dense because the particles can still stay in a confined area very well. Gases tend to be less dense, lighter, if you will, because the particles are able to move around and per unit area have less particles, therefore have less mass. Anyone who's ever moved water, right, picked up a jug of water when you're going camping, will tell you that liquids and fluids can be very, very heavy. Water is heavy. There are lots of solids out there that are lighter than water, at least from the look of what you are carrying. And this is important, especially when you get to engineering applications, understanding the pressures and understanding the force that a fluid can partake, not partake, the force that fluid can impart on something allows you to not allows you to make things that don't go boom. Right. Classic example here. Again, relating pressure and area and all that jazz. The reason a needle works the way it works is because it's super, super small, right? You don't put a lot of force into a needle in order to have the needle pierce your skin. If I want to pierce your skin with my finger, that would take a lot of force, right? That's how that game is played. There are equations for all these things. Again, the book goes over them. I'm not going to go super in depth into the individual equations because that's why the text is there. Read the text. Density is mass per unit volume. There you go, right? Here's a chart going over common densities of XYZ thing. You will again notice the gases are a lot smaller than the liquids, which by and large tend to be a lot less than the solids. But read the text. I'm not going to go over this stuff in depth individually. I want you to read the text and understand it. How does pressure work? For example, a gas. Well, a gas, so a solid doesn't exert pressure because the particles in a solid don't move. Okay. A liquid exerts pressure kind of in what it's touching based on how much liquid there is. A gas will insert pressure in the entirety of a container based on how much gas you put in there. Inflate a tire too much, it explodes, right? A gas pressure is dictated by the bouncing around of the particles. This is stuff that should seem very familiar to you because this is the kind of conversations you probably had in high school physics. The main difference, I guess, to surmise between the gas and liquid pressure-wise is a gas, as shown here, exerts equal pressure throughout whatever you're measuring, versus a liquid's pressure is determined by how much liquid there is. The top of the swimmer has less pressure on him than the bottom of the swimmer. Therefore, the pressures are equal, right? Pressure is exerted in both places, but the liquid, since it does not fill whatever it's in, exerts unequal pressure. Gravity plays a factor, essentially. Whereas with a gas, gravity is most times going to be negligible unless the container is that massive. And right here is an example I'm talking about. Let's go to the book to go through some math behind that. So 11.3. Again, I'm going to keep saying it. Read the book for these examples more in depth. Because I just passed equations there, right? But I did choose a question that goes through some of these equations right here. The pressure and volume, mass, area, height, everything related right there. So 11.3, calculating the average pressure and force exerted. What force must the dam withstand? So from a previous part of the book, you calculate the mass of a water in a large reservoir. Using that information, we will now consider the pressure and force acting on a dam retaining said water. as shown here, right? So you know what a dam is. The dam is 500 meters wide, and the water is 80 meters deep at the dam. That's the average pressure. And then what is the force exerted on the dam compared to the weight of the water in the dam, which we previously found the weight of the water as the force of the water at 1.96 times 10 to the 13th newtons. So we want to know pressure, and then we want to know force. All right. Do we have pressure? Well, yeah, you can find pressure. I say it's every chapter, right? Go back through the text and find the equations that have what you need to solve. For example, we know the width of the dam. We know the height of the dam, 80 meters and 500 meters respectively. And then we also know the density of water, because that's what that table we talked about before. So you can determine pressure given height, density, and gravity, or what's shown here. As pressure, give the information. So solve out. The height of the water is 40 meters. The density of the water is 10 to the third kilogram per meter cubed. And gravity is, of course, 9.8 meters per second squared. Measure all that out. You get 3.92 times 10 to the fifth Newton per meter squared, which we're going to calculate back out to a commonly used term, the Pascal. Again, covered that back in the book. Read the book, please. I keep saying that because that's the best way to learn this stuff. 392 kilopascals. That's a lot of pressure, but it's also a dam, right? So that's kind of obvious. If we're going to relate that amount of pressure to force, we need an equation again that does that. Lucky for us, force is given by pressure times area. So when we learn the area, which we can again calculate because we know its width and its height, therefore we can determine the area. That's just a two-dimensional shape, right? Multiplying those two out gives us 4 times 10 to the fourth meters squared for area. Multiply that by the pressure that we talked about before, that is at 1.57 times 10 to the 10th newtons of force. Noticeably, that is small compared to the force that we determined, or we're told about, that we would have determined from 1.1, 11.1, that 1.96 times 10 to the third newtons of weight water. 10 to the 10th versus 10 to the 13th, hugely different, right? 0.08%. Not 0.08% difference. A lot of this has to do with the width and depth of the dam. And, right, if this was a more complicated question, we'd be caring about the shape of the dam too. There's a reason why dams are wider at the bottom than at the top. But yeah, point of me wanting to go through that example is to re-emphasize to you, as if you're watching this video, that just find the equation solved. This chapter is actually pretty straightforward. So moving on. Something to keep in mind when we're dealing with reality is atmospheric pressure. Atmospheric pressure is the pressure put on us by the atmosphere. It relates to how high you are up from sea level, technically, usually. We count that in atmospheres. Shocking, I know, right? One atmosphere is, as shown here, the weight a column of air exerts on you when you're, I believe, at sea level. So the more atmospheres you have, the more it's like more stuff standing on top of you. A column of air weighs 1 atmosphere at sea level. That column, I think, is 1 meter squared, right? Yeah, 1 meter squared weighs 1 atmosphere. And it's a commonly used measurement when discussing gases in this regard too. All right, so let's get on to the application most people are probably most familiar with when talking about fluids. That would be hydraulics, essentially, Archimedes' principle. And how this works is a fluid will not like to compress. Okay, so if you take this example here and you fill both of these reservoirs up with a certain amount of fluid, and so much so that they're full, and you apply some pressure on the fluid, the total the fluid has no place to go. It can only move. And the cool part about that is you can apply some force one on that small area of a piston there. They're calling them pistons. That's the term you're most likely going to see, right? When you push down on the left side of that figure, the right side moves up. But the right side is larger, so you kind of assume that you have to like push harder or something, right? You always have a give when dealing with machines. We talked about machines a couple of chapters ago. You have to give something in order for the mechanical advantage to exist. Well, pistons, funny enough, don't really work that way. Since pressure is equal between both sides, and we know from the previous example we just talked about, force equals pressure times area. If you have a small area and a small force, but the pressures are the same, you're going to result in a large force and if you increase the area on the other side, the force is going to increase a lot to compensate for that. So construction equipment, for example, front end loaders, that'll work very well for this. The hydraulics on front end loaders are relatively small compared to what front end loaders pick up. Even the bucket alone is incredibly heavy, but it just has these little pistons moving back and forth to do all the things that construction equipment does. Because the pressures in the system are the pressures in the piston are the same in all reservoirs of the system. I just used system twice there. Sorry. Since pressure is equal throughout a piston system, such as what's shown here, pushing down on one end results in an equal but opposite push up on the other end, and the math will dictate. Right, I'll go show the math. It's probably a lot easier than me just talking a lot. You can get a lot of work done compared to the work put in when you build the system. That's kind of what I'm saying here. I'll skip over my blathering and we'll get to the example 11.6. That'll probably solidify this conversation a lot better for everyone. Not Archimedes' principle, Pascal's principle. Why didn't anyone tell me? Bad teacher. So, again, we talked before about the equation of relating force is equal to pressure times area, right? So divide those things out. Pressure is equal to force divided by area. So if we have a situation where we have pressures that are equal, then you have F2 over A2 equals F1 over A1. So you get the same result both times. And if you change the forces, for example, then what you put in equals what you put out. And it is super useful because you can do not a whole lot of force over a larger area and achieve a larger force over a smaller area, for example. I'm going to go through I'm going to do example 11.6. I'm going to stop talking. 11.6 will explain what I'm talking about. Automobile hydraulic system, this is brakes, right? Modern disc brakes. Hydraulic brakes use Pascal's principle. Driver exerts a force of 100 newtons in the brake pedal. This force is increased by a simple lever and again by said hydraulic system. Each of the identical wheel cylinders receives the same pressure and therefore creates the same force output F2. The circular cross-sectional areas of the pedal and the wheel cylinder represent some A1 and A2 respectively. So given all the information, if you apply 100 newtons of force to a brake pedal, which is what your foot's doing, this acts on the pedal cylinder through a lever. Cool. We talked about levers back, mechanical advantage 2 or 3 chapters ago. A force of 500 newtons is exerted on the pedal cylinder. So that lever turns 100 from your foot into 500 into a cylinder, a piston cylinder. Pressure created in the pedal cylinder is transmitted to, again, your wheel cylinders, your disc brakes. The pedal cylinder has a diameter of 0.5 centimeter, and each wheel cylinder has a diameter of 2.5 centimeters. So the wheels have a lot larger area than the pedal cylinder. Calculate the force F2 created at each of the wheel's cylinders. So if I put 100 newtons down at the start of this conversation, what are the brakes feeling? What forces be applied to the brakes to stop the motion of the tires? So we were given an F1 that's applied to the pedal cylinder, which is at 500 newtons. Cool. We know the cross-sectional areas of these. So given that pressures are identical throughout, we don't have to worry about pressure, right? Since P1 equals P2, F1 over A1 equals F2 over A2. Cool. So solve out, figure out what we know. We know F2, we can rearrange this guy to solve for that force that is what we care about. And we know A2 and A1 because those are given to us already, right? They pi r squared. You don't even care about that because I give you the areas of what we're talking about. Divide out the math, and we get that your 500 newtons of force into the brakes yields a total stopping force of 1.25 to the fourth newtons. That's to the fourth, so that's 12,000 newtons of pressure out of 500 pressure in. You're going to divide that by 4, of course, going throughout. But brakes have a lot of stopping force, and it's all due to this pressure, lack of pressure differential, given the incompressibility of liquids. Super cool stuff. And as I said before, the math is pretty straightforward. Lucky us. There's lots of different ways to gauge and understand how pressure is measured. Right? When you fill up your air in your tire, you probably have one of those little stick pressure gauges that you put on the stem, and it shoots out how much pressure is in the air tire, right? Those are direct measurements of that pressure, the pounds per square inch, PSI. They work exactly that way. We've had lots of different ways in the past to measure these things. If you're playing with a chemistry set and stuff like that, this pressures can be important. Getting blood pressure, the cuffs measure how much, essentially when it squeezes it down, it's trying to stop the blood from flowing. And then as you ease up, the blood pushes back through, and the blood will push through the cuff based on how strong the blood is able to be pushed. And the nurse or the phlebotomist, whoever is measuring your blood pressure, is actually recording the pressure being felt back by the cuff with a timer to figure out how much blood pressure you have. And there's two measurements. There's your arteries pushing blood out of your heart, and your veins returning the oxygen depleted blood to your heart. And you actually measure both of those, funny enough, when you take your blood pressure. Arteries are a lot more pressure. Arteries have a lot more pressure than veins in them. But I'm not going to go super in depth in that. If you take a health class, you're going to learn a lot more about blood pressure than I'm going to teach in this class. I'm just giving you the basics here. Mercury barometers. A barometer is, of course, a measurement measures pressure, right? It's an old. Some of you may have like antique barometers or something at your house, or your grandparents' house. They're pretty cool. They tell you atmospheric pressure because you can tell when a storm's coming or something like that. Again, storms are another fantastic, interesting example of how pressure works in the real world. A storm front is literally shoving air forward. So pressures change when a storm is coming in, because the storm is like shoving everything around it, because storms are very heavy. They're full of water, right? That stuff's pretty cool. And I should go back to this example here. A mercury barometer, what it does is, as you can see, it is a tube with a vacuum in it at some zero pressure at the top there. And as the atmospheric pressure applies to the basin that the barometer tube is sitting in, that's going to move the I'm losing the word here. That tube in the center, that's going to move up and down based on the atmospheric pressure. And then that measurement is going to give you a very accurate measurement of what the, well, pressure is on the outside. I said pressure like 12 times there. This is probably a concept you guys get already. I'll move on. But yeah, fluids apply everywhere, pressures apply everywhere. Lots of examples go over the same thing here. Floating essentially is when you even out the pressures. It relates to the density of the object and how deep it is in the water. Most everything will float at some point. Well, not everything. Ocean's not going to float, obviously, but things will float based on their internal density compared to the water. Because remember, the deeper you go in water, the pressure gets more intense because there's more water stacking on top of you. When a fish, for example, changes its air bladder, its swim bladder, it's increasing or decreasing its entire average density of the fish, so it's able to rise and drop by adjusting its density by how much air it's holding inside of it. Right, the less air it's holding, the denser the average fish's body will become, and therefore it will sink. Buoyant force, that's what this is all going over. We'll go over an example 11.8, run through some of the math on that. Again, gauge pressure, absolute pressure, read the text. So if you're going through the questions, you're not quite getting them, I really want you to go through the text. That's going to solidify these concepts a lot better than me spending 2 hours talking over YouTube about it. You're still going to want to go through the text for your double checking. So go there. Archimedes' principle was buoyancy. Pascal's principle was pistons. Yeah, sorry about that. All right, calculate buoyancy force depending on shape. Calculate the buoyant force on 10,000 metric tons of solid steel completely submerged in water, and compare this with the steel's weight. All right. What is the maximum buoyant force that the water could exert on the steel if it was shaped like a boat that could displace 1 × 10⁵ cubic meters of water? So essentially, things float because of their shape and the pressure, how much area it takes to the fluid to apply its pressure to. A cube and a boat, or a cube and a plate of the same weight will obviously float very differently. That's because, well, actually, I'll go back to this example. What am I on? 20. I'll go back to this example way up here. You see all those up arrows? The more up arrows you have, the more things you have pushing up, right? A boat works, or someone just floating in the water works, because they have a lot of up arrows pushing up. If you decrease the amount of up arrows, you decrease the amount of force pushing up. That's floating. Up arrows. Go back to 20, and then go back here. Cool. So we do have equations relating to all of these things. For example, density is mass times volume, right? So you can figure out the steel's volume based on those conversations. Its mass, its density, 7.8 times 10⁵, from that chart we talked about way at the beginning of this video. To get a volume of steel, the volume of this particular steel here is 10,000 metric tons of steel at 1.28 times 10⁵ cubic meters. Because the steel is completely submerged for the example, this is the volume of the water displaced. What is water displaced? Well, it is exactly what it sounds like. If you submerge something, the water that was there has to go someplace. Usually goes above you, right? If you can actually measure something's volume perfectly by measuring how much water it is displaced when it's submerged. So displaced water is exactly what it sounds like. It's the water that's moved by you being submerged. So we can now find the mass of the water displaced from this relationship between its volume and density, which is given by the mass is the volume and the density, right? It's just rearrange the equation we used for 11.32. And that gives us a density of water is 1,000 kilograms per cubic meter. We know the volume of the cube, so therefore we know the volume of the water displaced, to give us a mass of 1.28 times 10⁶ kilograms. That's how heavy the water is that was displaced by this cube being dropped in it. according to Archimedes' principle, which is an equation talked about up here. There you go. The buoyant force is given directly by the weight of the fluid displaced by the object. You know how heavy the water is that left. That's how much buoyant force. That's how much. The more water that leaves, the more buoyant force the thing has, because that's the amount of up arrows that I talked about before. So how much buoyant force exists for this cube? About 1.3 times 10 to the 7th Newton meters. Cool. Well, given the steel's mass at 9.8 times 10 to the 7th Newton meters, you're going to have the weight, the downward force of the steel due to gravity exceeds the buoyant force of the water pushing back up on it. Therefore, this thing's going to sink. If we do the same conversation with a boat, we're going to notice a couple of different things. First and foremost, here you have 1.28 times 10 to the 3rd displacement of water. But here you have 1 times 10 to the 5th displacement of water. You displace a lot more water in the boat because it's a lot larger. So when you do that, you get a larger buoyant force because you've moved more water. There's more up arrows, right? 9.8 times 10 to the 8th buoyant force for a ship against the 9.8 times 10 to the 7th weight of the steel it takes to produce it. So you have an entire order of magnitude more buoyant force, a lot more arrows pushing up because there's a lot more water with upward force that the boat is touching. Therefore, the boat floats. There you go. There's math. There's the math of boats. I knew taking this class would be beneficial for you. That is how buoyancy works. Going to a couple more examples. This is specific gravity is cool. That is something's relation to water, how dense it is compared to water. It's a commonly used. It's a way. If I tell you something specific gravity, I'm basically telling you its density or how heavy it is, but I'm using a more scientific term because I'm comparing to water. Lots of things in science, of course, you've seen through this course are compared to water. How heavy something is the same. And this picture here goes over, as I said before, density measurements of things work basically perfectly with water because we set water equal to 1. Then water has density of 1. So therefore, things that are lighter than water have less density, greater than water, more than 1. And the displacement theory we're talking about with Archimedes' principle kind of let you know exactly how much something weighs. And you can, for this example here, using that to determine body fat percentage and stuff like that. Examples I'm not going to go over in this text, but the ways that some of you in the professional world may use density and may use fluids. This is from a question about determining what a material is made out of based on how dense it is. Now you can weigh an object, but you're not getting a good understanding of its density when you weigh. Just know how heavy the thing is. Density will take into account how big the thing is as well. So this is something actually silver is what this picture is going about, and is a example from the text. All right, last thing it covers is a couple of various topics on expanding on what we've talked about. Things such as bubbles work through cohesive forces of molecules. It's more of a chemistry thing than a physics thing, really. Well, it's the physics of chemistry, so it's still interesting, but we're not going to go so deep into that. What is this guy here? Surface tension. Surface tension relates directly to that cohesion of the molecules we talked about before. Things don't like to break, right? When you go into water, you're essentially breaking the loose connection that the fluid has, loose connection that the liquid has, keeping it together. You're separating the molecules, essentially. How do you not break surface tension? Well, you increase area. That's exactly how that stuff works. Or you decrease force. As shown on the left there, A when you see bugs walking across water, not sinking, that has a lot to do with the amount of surface area that the bug is taking, in the sense that the foot of some of those water skimmers and stuff like that are pads, or they're geometric shapes, not just points. So that allows them to cover more area and therefore not break surface tension. Surface tension as well has a there's equations to all this stuff, and they're kind of variations on what we've already talked about, which is why I'm skipping them. Yeah, these are just more examples going over the same principle, so I'm not going to go too deep into this stuff here. Yeah. This is the thing I wanted to get to actually at the end here, was a application related to biology. I know a lot of you students are probably taking this class as a prerequisite for your biology degrees, going into health sciences and stuff like that. And pressures play a very, very important role in understanding the mechanisms of living things, right? Obviously humans have pressure in them from blood and all that, but your oxygen, your lungs work based on pressure differentials. You go into nature, that's how water gets sucked up to the tops of trees as pressure differentials. You're not you're not physically moving. Trees are not like inhaling, exhaling to push the water and the nutrients from the soil up to the leaves. You're actually having a negative pressure being created at the top of trees. It's fascinating stuff. Look into it sometime. But all of these equations and topics we talked about directly, very, very smoothly and directly relate to the various applications we're going to be running into. You're going to be running into as you go throughout your professional career. So it's more about surface pressure. Again, not super interested in this conversation. It's cool stuff, don't get me wrong, but there's not really that much, I don't know, interesting math to it, I guess, would be the thing I'd have to say. See, I can show you some of the stuff here, but surface tension is, again, defined based on the material you're talking about. This Greek letter, I can never remember what that one is even called, but it's directly related to force and the force you're applying. Surface tension is related to the force you're applying, and the area or the length or some unit of displacement measurement that you're trying to pierce through. So it's directly related to pressure. Again, this is why I'm skipping a lot of this stuff, because it's just, this chapter is all straight equations. So last thing I wanted to discuss was an example of that capillary action, 11.8, 11.12. There we go. Where you at? Here we go. Yeah, the tree sap example. There we go. Can capillary action be solely responsible for sap rising in trees? Was capillary action? That is that. Here we go. Tendency of a fluid to be raised or suppressed in a narrow tube or capillary tube is called capillary action. So it relates the pressures that we were talking about before with the pistons, right? If you put something in a small tube, it tends to rise larger than you'd think, because the surface tension that would cause the water to break and slide back down is higher, because there's more stuff touching the water, right? So you have more surface tension, essentially. That's capillary action. Let's take a look at that capillary action in response to a tree. Calculate the radius of a capillary tube that would raise sap 100 meters to the top of a giant redwood, assuming the sap's density is 1050 kilogram per cubic meter. Contact angle is 0, and the surface tension is 20. It's the same as water at 20 degrees Celsius, which is a given from the chart up here. Here's your surface tension, contact area conversations. So height raised due to capillary action is given by an equation shown there, with that weird looking Y thing being that surface tension of the material that we're talking about. In this case here, surface tension was water at 20 degrees, so cold-ish water, right? 20 degrees Celsius at 20 degrees Fahrenheit. Gives you, and this 0.0728 Newton meters of surface tension or grab of the water, if you will. Throw the rest of the equations in there, and you get a R, or the quantity of. Sorry, let me read this again. How the water is gathered and every cornerstone for all substrate. All gives you 1.14 times 10⁻⁷ meters of. Oh, that's the size, the radius of the capillary tube. How big the capillary tube would be in order to shove the sap or the liquid up that high based solely on that like surface tension conversation. And when you look at that number, that's right pretty small. That's a very tiny little tube. If you had a tube that was that wide, 1.41 times 10⁷ meters, and you put that in water, the water would rise 100 feet up the tube based more or less purely on surface tension. That's what that's saying. However, the capillaries, or the stuff in the tree that water flows through isn't actually that small. The xylem, I'm going to call that, in trees is in fact 2 degrees larger in radius than what is two orders of magnitude larger in radius than what we calculated. So capillary action, just that surface tension movement, is not solely what pushes liquids through a tree. And yeah. So other things to discuss as we end this chapter: you can have negative pressures if you break a piston's pressures, for example. Negative pressure sucks in as opposed to pushes out. I'm sure you're all familiar with negative pressure. You played with those water guns that you put the water gun in the bucket of water, you pull it backwards to fill it up, right? If you do that incorrectly, it's going to be a lot harder to push forward because you have negative pressure caught. It's summer things. It's winter as we're recording this, so been a while since I've done anything fun like that. This is what I was talking about before with the arteries and veins conversation. Notice the pressures in the arteries in the red on the right are 120 milligrams of mercury, a lot higher than the 25 milligrams of mercury of the veins that's bringing the oxygen depleted blood back in. Cool. Pressure tests for eyes and all that jazz, and how pressure works with lungs. I suggest if you care about this stuff and it's applicable to you, go ahead and read chapter 9. It is fascinating, the different ways pressure interacts in the body and the uses of Pascal's principle and stuff like that allow our body to exist and function the way it does. It's super cool stuff. Just the difference between a deep breath and a shallow breath, right, it's fun. And that is fluid statics. Biggest takeaway I want you from this is the equations are super simple and not really related to stuff we talked about before. So that's pretty cool. I hope you enjoyed the conversation, and take care.